Have you ever stopped to think about what's holding the entire universe together? Like, at the most basic fundamental level? Well, we're going to talk about the unsung heroes of particle physics, the particles that act as the universe's strongest glue. They're called mesons. And their story? Well, it all starts with a huge puzzle.
So it all kicks off with this really simple but kind of mind-blowing question. If you look inside an atom's nucleus, you've got all these protons, right? And they're all positively charged. Basic physics tells us that like charges repel, so all those protons should be pushing each other away with incredible force. Logically, the nucleus should just fly apart. It should be totally unstable. But it doesn't. So what's going on?
The reason everything stays locked together is because there's another force at play, a force that's way, way stronger than electromagnetism, at least over these super tiny distances. This is the strong nuclear force, and it really is like a cosmic superglue. But, for a force to actually do anything, it needs a particle to carry it. So the next big question was, what particle is doing all this heavy lifting?
Okay, so picture this. It's 1934. And a brilliant physicist named Hideki Yukawa has an idea. He theorizes that there has to be some undiscovered particle that's responsible for this force. He imagined protons and neutrons playing a sort of game of catch, constantly tossing this particle back and forth, and that exchange is what holds them together.
And Yukawa didn't just stop there. He actually calculated what its properties should be. He figured its mass had to be somewhere in the middle, intermediate, between a super light electron and a much heavier proton. And because of that, he gave it a name, the meson, from the Greek word mesos, which literally means middle. And just like that, the hunt was on.
But of course, in science, it's never that easy, is it? The road to actually finding Yukawa's meson had a major unexpected twist. It turned into a real head-scratcher, complete with a classic case of mistaken identity.
So just 2 years after Yukawa's prediction, physicists discover a new particle, the muon. And hey, it had roughly the right mass. Everyone thought, that's it. We found it. We found the meson. But there was one huge problem. The muon just didn't care about the strong nuclear force at all. It was basically just a heavier, unstable cousin of the electron. It took another whole decade, until 1947, for a team led by Cecil Powell to find the real deal, the pion. And this particle did exactly what it was supposed to do. It felt the strong force. It was the true meson.
So just think about that journey for a second. From a pure idea on paper to the final discovery, it took over a decade. You can just imagine the frustration and then the excitement. First, you think you've got it with the muon, only to realize it's a complete red herring. Then, years later, the real particle finally shows up. It's just a perfect snapshot of how science actually works. You get a brilliant prediction, a messy search, and then finally a Nobel Prize-winning discovery.
All right, so that's the awesome discovery story. But what actually is a meson, according to what we know today? To get that, we need to zoom way in and look at the fundamental ingredients that they're made of. Let's start with something we all know, a proton. Protons, and neutrons too, belong to a family called baryons. And the one rule for being a baryon is simple. You have to be made of 3 quarks. This 3-quark setup makes them part of an even bigger group called fermions. And you can just think of fermions as the solid, stable bits that make up all the matter we see and touch.
Mesons, on the other hand, follow a totally different recipe. Instead of 3 quarks, they're made of 1 quark and 1 antiquark, which is the quark's matter-antimatter twin. This unique quark-antiquark pairing puts them in a different family called bosons. And unlike fermions that build stuff, bosons are the particles that usually carry forces, exactly like Yukawa predicted.
So there you have it, the modern definition. A meson is this special combo of a quark and an antiquark. But the real key thing to remember about them is that because they're part matter and part antimatter, they are incredibly unstable. They don't stick around. They pop into existence for just a tiny fraction of a second to do their job, and then poof, they decay into something else. They're the temporary messengers of the strong force.
But here's where it gets really fun. The pion? That was just the beginning. It turns out that meson isn't one particle. It's a whole huge family of particles, and some of them are pretty wild.
I mean, just look at the variety here. Quarks come in different types or flavors, and you can mix and match them. The pion is made from the lightest quarks, an up and an anti-down. But what if you swap one of those for a strange quark? Then you get a chion, which is a lot heavier. And if you go all out and build one from the heaviest quarks, a bottom and an anti-bottom, you get the upsilon, a real heavyweight champion of the meson world.
And just to put that in perspective for you, the upsilon meson is about 10 times more massive than a proton. A proton, the thing made of 3 quarks. The upsilon is just 2 particles, a quark and an antiquark, and it's 10 times heavier. That just gives you a sense of the incredible amount of energy that's locked up inside these fleeting little particles.
So, you might be thinking, okay, we've been at this since the 30s, surely we've got it all figured out by now. Well, not even close. The study of mesons is still very much at the frontier of physics, pushing the boundaries of what we thought was possible and leading to some truly exotic finds.
For decades, the rule was so simple. 1 quark, 1 antiquark. That's a meson. But physicists love to ask, what if? What if you could stick more together? And what's incredible is they found them. They've now confirmed particles like the Z4430 are tetraquarks. That's 2 quarks and 2 antiquarks all bound together into 1 exotic meson. This literally opens up a whole new chapter for understanding the strong force. So we started with a really simple question about why the nucleus doesn't just explode, and we've ended up at the absolute cutting edge of particle physics, talking about tetraquarks. It really makes you wonder, right? If mesons are the glue holding all the regular matter together, what other strange and amazing particles are still hiding out there in the quantum realm, just waiting for us to find them?